Welcome, guys. Today we are going to be looking at population ecology, our third installment in our ecology session here. And we are getting down to the end of the required content that we must cover. So population ecology is one of the last topics here. So we want to begin by just talking about what a population is. Talked about communities, we've talked about ecosystems. Now we're looking at populations, and these are going to be all members of one species in an area. So all members of just one species in an area. Remember, a species is going to be a group of organisms that must be able to breed and produce viable offsprings. So when we're talking about a population, two different ways that really groups or organisms will enter a population. They're going to enter via being born into that population, births. We're not necessarily talking about humans here, but we could be, or they could come in from another group. We call immigration, right? And we call births typically natality. Birth rate is natality, and people will leave, or organisms will leave via deaths or mortality, and just leaving the group or the population. Immigration. So if we take both of these kind of concepts and combine them, we can calculate what's called PGR, or population growth rate. PGR, that's going to represent our natality, which is our birth rate, and the immigration rate. And then we're going to subtract from that the death rate or mortality and the number of individuals leaving the population. And that'll give us our PGR, population growth rate. Now, there's other ways that we can somewhat calculate this, and we could think of this as kind of the change, the change in the population number over time, the change in time, right? And that should equal our birth rate minus our death rate. So that's another way that you might see that. For us, this first piece here is plenty good enough. So we're going to talk about and look at something called age structure pyramids. Age structure pyramids. Age structure pyramids. And we'll get a look at what these are. So here we're looking at some different age structure pyramids. And what we have here are different age groups that have been broken down, male and female, for different countries. And what we can see is in this blue zone, this is what's called a pre-reproductive age bracket. So ages from 0 to 14 broken down into 5-year increments, 0 to 5, 6 to 10, and then 10 to 14 or 10 to 15 here. All right, and we see that across the country spectrum continuum here. The greater the size of that base, the more rapidly growing the population is going to be as those individuals in the blue zone in the next decade or 2 decades transition into the reproductive age group, which are the yellow brackets. And then the reproductive age group will transition into the red or the orange band, which is the post-reproductive age bracket. So a rapidly growing country will have a large pre-reproductive base. Slow growth, which is the United States, very slow growth, according to the last census, will have a slightly larger base, but then it tapers upwards. Zero growth, like some countries in Europe here, would have pretty much a flat, parallel base pre-reproductive with reproductive age bracket, and then taper at the top. And then a negative growth country, you would have few individuals in this pre-reproductive age bracket. And it would taper kind of like an upside down pyramid. So again, rapid, slow, zero, and negative growth. This is what that would look like if you mapped out everyone's age and put them into one of these bins. So a lot can be learned in terms of policy and decision making by government and planners based on where the bulk of your population is at. We're going to look at a couple different ways that populations tend to grow. And the first way will be what we call exponential growth. Exponential growth. We're going to go ahead and graph this out so we can see it. So here's my y-axis. Here's my x-axis. And I'm going to have the size of the population over here. Sometimes we'll just use a variable n for that. We'll have time, or t, down here. And what we would see is that an exponential growth start at the origin times 0, and the population begins increasing, and we see this rapid increasing growth. If a population is going to grow like this, you would expect that there is no resource limitation. Now, it's unlikely that a population would experience these conditions for very long, so most populations cannot grow this way indefinitely. So we'll say most populations can't grow this way or grow exponentially forever or indefinitely. There's going to be a cap when resources become limited, and we talked about limiting factors. What we could do is we could kind of take 2 points in time here. So let's say that we took this point in time and this point in time, and we wanted to figure out what that growth rate is. So the growth rate here is what we call R. And there's an equation that we can use to figure that out. If you're working with a software program, you can make a line, a best fit line here, and then just find the slope. We know that y equals mx plus b. So if you were to make like a best fit line in here, you could find that slope value there and have a good idea of what the rate would be. We don't even need to worry about what the actual equation is for finding this. Just because you're not really going to be asked to do that. You would want to know, that slope, rise over run, delta y over delta x would be how you find that, but that's something that you're not going to have to be too concerned with. So exponential growth is one type of growth pattern. The next type of growth model we're going to look at is the growth model that occurs when those limiting factors start to play a role. We call this logistic growth. Logistic growth. So we're going to make our plot, begin it the same way. We'll have, again, size of the population. We'll have time down here. And what we're going to see is this growth begins somewhat like before. So it begins somewhat exponentially, but eventually those limiting factors start to play a role. And we overshoot up to a certain point and then kind of flatten out. That's what we call logistic growth. Now, this line that we approached and kind of overshot represents the amount of organisms that this environment can support. And we call this line K. As the variable of K, and it represents our carrying capacity. And this carrying capacity is the number of organisms a habitat can support indefinitely. So based on the resources, the competition, the other groups there, how things are being partitioned, that all affects our carrying capacity. So again, this type of growth assumes that resources are limited, so we don't have unlimited resources, and the population can either way overshoot and then crash back way below the carrying capacity and way overshoot and crash back down, which is what we see with insects and some other types of species, fish, some reproduce that way. Or we could have the population just come up to the carrying capacity and just kind of oscillate right along there. And we see that with other organisms. So again, this is more of a realistic type of growth pattern. So this is more realistic growth. And there's a whole equation, for this as well, but we're not really going to need to focus in on that. What we do want to look at are some things we call reproductive strategies. So reproductive strategies. Reproductive strategies. So we've got what we call K-selected. And what we'll do is we'll just make a kind of a table, we'll bisect this space in half. So we'll have K selected, and then we'll have R selected. And our K selected, that comes from this variable K for carrying capacity. So again, what we'll say is K selected, they display features or traits for living at population densities. So they display traits for living at population densities close to the carrying capacity. So they're going to display traits for living at densities that are really close to the carrying capacity. So you're not going to see much swings above or below the carrying capacity line. So an example of this would be something like a rhino here, right? Where they have few offspring, they have a quite large body size because the resources are being used in a fashion that allows for this type of size. They have a pretty long lifespan because their conditions aren't changing or very dynamic. And they can invest extended parental care because that offspring lives a long time and they don't have very many of them. So this would be something that we would see with a K-selected group. So we'll go ahead and just make a note here. A rhino wouldn't be the only example. There'd be plenty of others, but that's one that we can just kind of make a note of. And again, we would be looking at things like very few offspring, probably a long gestational period, large body size is allowed in this setting. Lifespan is going to be longer. It's going to be a while for those organisms to move from the pre-reproductive age to the reproductive age bracket, and we'll have extensive parental care. On the other side, we're going to be looking at R selected, and this R represents growth rate. So they're going to maximize growth. So the strategy is going to be to maximize growth when conditions are appropriate. So maximize reproductive success or growth, population growth at low population densities. So when population densities are low, these organisms are going to try to maximize their success and increase their numbers in great amounts. So an example of that is a lot of insects, right? So here are some periodical cicadas that are on like 7 or 13-year cycles, and population densities are almost zero when they emerge at the end of the 7-year cycle. So they're going to maximize reproductive success and maximize, breeding opportunities and have a whole bunch of population, and then you're going to have a huge crash. So this is that boom and bust, going way above the carrying capacity and then dipping way below the carrying capacity. So we'll go ahead and make a couple notes of that here. Again, you're looking at things like insects. Certain types of insects do this, certain sorts of fish or aquatic organisms. So again, what we're looking at here is you have a rapid growth rate. So almost no time spent in the pre-reproductive years. Maturity, so rapid growth rate, really quick to mature. We've got short lifespan, so they don't live very long, maybe one season even, however short that may be. Body size typically isn't allowed to put on a lot of mass because they don't live that long, so they're typically small. Huge numbers of offspring. So lots of offspring because a lot of them don't survive. And then typically spread over a really large area, large dispersal. Now what we'll see is not all organisms fit into these two groups. Some organisms are kind of a continuum that span both. For instance, if we look at a sea turtle and we kind of evaluate what sea turtles do, they have a whole lot of offspring, like are selected. The growth rate is quite slow, which would be K-selected. They have a long lifespan, like K-selective. They don't invest much parental care, like an R-selected. There's a large dispersal, and there's almost no parental care. So again, that kind of spans both groups. So what we would say is you're going to have organisms like a sea turtle that have features of both. And again, this is going to be natural selection is going to shape some of these features of these groups to maximize their success in response to selective pressures. So earlier we used this word limiting factors. And exponential growth was in the absence of these limiting factors, and logistic growth was when we had these limiting factors. So let's talk about what these limiting factors kind of take the shape of. So we have one group that are density dependent limiting factors. So population density dependent limiting factors. So with these limiting factors, population size matters. The greater the population, the more impact they're going to have. So the greater the population size, the greater the impact. So think about this, as population goes up, things like competition increases. So competition is going to have a greater impact at population numbers that are large. You have territory becomes more scarce, so you have territoriality, where they're again competing for territory. You have disease that spreads easier with greater population numbers. You have predator-prey relationships. So predation goes up with greater density numbers. Stress can go up with greater density numbers. So those are density dependent factors. The other group will be things we call density independent. So these things are going to limit population sizes regardless of how big it is. So the population size has no effect. So these are going to be more climate based or topography based or resource based. So again, these are things that are resource based. But again, resource in terms of availability, probably. Not competition for resources, but just availability. Or you could have things in here like just natural, disasters, where it doesn't matter how large the population is, it's going to be impacted. So those are limiting factors. Let's talk about distribution. So distribution. So here you're looking at three different ways populations can be distributed. So we have kind of a uniform distribution pattern, we have a random distribution pattern, and we have a clumped distribution pattern. So the uniform is going to be where the habitat is somewhat uniform in nature, and the organisms, don't have a selective advantage at one particular spot or the other, so they uniformly make use of this landscape because it's pretty much the same. With random, the population is going to be distributed in a way like these wildflowers, these dandelions, where they land is where they germinate, and they don't have the ability to move from point A to point B once they have become established. Clumped, you're going to see social animals that are herding around resources because the distribution of these resources are not uniform in the environment. So let's go ahead and just make a note of this. So again, you're talking distribution could be uniform, can be clumped, or random. So the question is, how do we go about measuring population size? Now with the plants, right, you can go and do this and take an average per square meter or, per square mile. So you can measure plants with some ease. When it comes to animals, it becomes a little more difficult. And there's a method that we call mark recapture. So mark recapture. And we're going to talk about how we make use of this. So let's go ahead and get a look at this. On the left, we have this individual fishing in a closed water source, a small pond or a pond, and they are going to catch 10 fish, right? And that's what we see here in the pink. And they're going to tag them or mark them and then release them back to the pond. They're going to wait a determined amount of time, a year, 6 months, whatever, come back and then fish again. Same, and they're going to fish for the same duration. And let's say they catch this time 10 fish, and 5 of those fish happen to be marked from before, and 5 are unmarked. So we can use that ratio to help us determine what an estimate would be for the original population size. So we'll look at an example here. So let's say that we have, you'll put the equation up here. So mark recapture, the equation looks like this. So we have our mark or our tagged individual over our total population. And that should be equivalent to the ratio of our recapture mark or tag over the total recapture. So we can use kind of a proportion. So let's say that we have 100 acres of space, right? An acre is like a football field without the end zones. And let's say that in 2020, we went out in our 100 acres and we caught 250 squirrels. And we tagged them and then we released them. So tagged and then released. And then we came back in 2021 and then we sampled. So let's say we did this for 3 weeks. Same number of cages distributed in the same places. And this time we caught 200 squirrels total. And of that, 130 were marked from the previous capture period. So what we would do is set up this ratio. So we would say that we had 250 squirrels that were tagged, and we don't know what the original population was. That's what we're trying to figure out. When we did the recapture, we had 130, and then we captured 200 total. So we cross multiply here, 250 times 200, divide by 130, and our estimate is about 384 squirrels. And that's a mark recapture study, and that's how it's done in ecology. So that is population ecology. I hope that's helpful. I'll see you next time.